Hi everyone. So now we're going to start section 11.5. Just a quick recap. Remember we talked about the product and quotient rules, and we also talked about the chain rule before spring break. So now what we're going to do is we're going to talk about the derivatives of logarithmic and exponential functions, and we're going to incorporate some of the rules we learned before with what we're learning now. So first things, derivatives of natural logarithm and logarithm with base b. Thus, this is called the natural log of x. Prime means derivative. The derivative of the natural log of x is equal to 1 over x. The derivative of log of x base b is equal to 1 divided by x times the natural log of b. The derivative, this is just using Leibniz notation instead of prime notation. The derivative with respect to x of the natural log of u is equal to 1 over u times the derivative of u with respect to x. This is just illustrating the chain rule, because whenever you're saying, hey, this is the natural log of u, I need to differentiate it with respect to x. Well, there is no x here. So we first have to differentiate this with respect to u, which is 1 over u, and then multiply that by du over dx. So the derivative with respect to x of log of u base b is equal to 1 divided by u times the natural log of b times the derivative of u with respect to x. All right, those are our rules. So now let's look at some examples that are applications of those. So we want to find the derivative of the function for all of these parts here. And they're problems chosen from your homework, from your homework set. So f of x is equal to the natural log of x plus 3. Okay, we want to find f prime of x. So f prime of x is going to be equal to 1 over x plus 3 times the derivative of x plus 3. That's going to be 1 over x plus 3 times 1, because the derivative of x plus 3 is 1. So you end up with 1 over x plus 3. That's the derivative. Now, so that was an application of the first rule. Now let's find the we're given the log of x base 3, let's find the derivative of that. Now what you should do is write all of your rules down, or flip back and look at your rules while we're taking the derivatives. It'll make this much easier so you can see it applied. Okay, so f prime of x is equal to 1 over x natural log of 3. That's it. Now, here in part C, we have r of t is equal to the log of t plus the square root of t base 3. And we want to find r prime of t. For this rule, or to take this derivative, we need to remember rule 3 from page 1, which said not rule 3, but rule 4. We need to remember that the derivative with respect to x of log of u base b is equal to 1 over u natural log of b times the derivative of u with respect to x. That's what we're going to apply in part C. Well, just so you see it, this t plus the square root of t is our u here. So, knowing that, we get 1 divided by, parentheses, the quantity t plus the square root of t, natural log of 3. That's just direct application of this part over here. Remember, b for us is 3. And then we're going to multiply that. Now it says, the other part of our rule over here says to take the derivative of u with respect to x, or u prime. So that's going to be times the t, that shouldn't be the square root yet. This should just be t plus the square root of t prime. Now, that's equal to 1 divided by t plus the square root of t, put that in parentheses, times the natural log of 3. And then the derivative of t is 1 plus 1 over 2 square root of t. So just a quick refresher or reminder, so an aside here. Remember that whenever you're differentiating t plus the square root of t, you are using that the derivative of a sum is the sum of the derivatives. So you'll have that's equal to t prime plus t to the 1/2 prime. The derivative of t is 1 plus 1/2 t to the negative 1/2, which we can rewrite as this. Okay, so it turns out that this is our final answer. Okay, now let's find the derivative of this function here. So you have the natural log of 9x over 4x minus 2, and we want to find the derivative of that. So to differentiate this function, you can do it a couple of ways. You can either use part 1 on page 1, coupled with the quotient rule, or you can rewrite it using the laws of logarithms, which would be easier in this case. So we can write this as the natural log of 9x minus the natural log of the quantity 4x minus 2. Remember that law of logarithm that says, hey, if you're taking the natural log of x over y, that's equal to the natural log of x minus the natural log of y. That's the rule that we're using below. That's the rule that we're using right here. So we haven't differentiated yet. All we did was rewrite it. Now, to differentiate this, we have to use rule 1. So we have 1 over 9x times 9x prime minus 1 over 4x minus 2 times the derivative of 4x minus 2. Well, that gives us 1 over 9x times 9 minus 1 over 4x minus 2. The derivative of 4x is 4. The derivative of negative 2 is 0. So this gives us 9 over 9x minus 4 over 4x minus 2, which we can simplify and write as 1 over x minus 4 over 4x minus 2. And that's our final answer. Now that we've talked about the derivatives of logarithms, we now want to learn more rules and talk about the derivatives of exponential functions. The derivative of e to the x is e to the x. The derivative of b to the x is equal to b to the x times the natural log of b. The derivative of e to the u with respect to x is equal to e to the u times the derivative of u with respect to x. This is the chain rule. The derivative with respect to x of b to the u is equal to b to the u, natural log of b, times the derivative of u with respect to x, or in other words, u prime. Now would be a good time to pause and write all of your derivative rules down on one sheet, because from this point on, we are now going to first go through examples of these, and then we're going to go through examples that require you to use your new rules that we're learning here, coupled with the product rule, quotient rule, and chain rule. Okay? Note that the derivative of b to the x is not x b raised to the x minus 1. That's a common mistake the students make. Make sure you do not make that mistake. It's not the power rule. The power rule only applies to constant exponents, not variable exponents. Okay? So, for example, let's find the derivative of the function g of x equals 5 raised to the x. what rule are we in above? If we look back up, it's not e to the x, but hey, this looks just like b to the x, except for b for us is 5. So the derivative is equal to 5 to the x times the natural log of 5. That's it. That's our derivative. Now, if we have h of x is equal to 3 raised to the x squared minus x, let's differentiate that. Well, looking back up, this looks like we have a u here because we have a function x squared minus x instead of just a variable like x. Okay, so we need to use rule 4 here. Well, u is going to be equal to x squared minus x. So differentiating that using this rule down here, we get 3 raised to the x squared minus x times the natural log of 3. But then we have to remember to multiply that by the derivative of u with respect to x, or in other words, that prime. Rewriting that, we get 3 raised to the x squared minus x times the natural log of 3, and then the derivative of x squared minus x is 2x minus 1. Okay, so this is our final answer. Okay, so on the side, remember that whenever you're differentiating x squared minus x, that's equal to the derivative of x squared minus the derivative of x, and that's equal to 2x minus 1. Okay? Now examples continued. Now what we're going to do is we're going to use a combination of those rules. Right now we don't have to. For this example, we have to differentiate e raised to the x squared. So we have the derivative is e raised to the x squared, but we have to remember to differentiate x squared. So we get e raised to the x squared times 2x, or just rewriting it to make it look nicer, 2x e to the x squared. Next, we have r of x is equal to e raised to the 2x squared cubed. That is e raised to the 2x squared cubed. So notice here that we have a combination of functions. There are a couple of ways you can do this. You can either use the chain rule, which it would be the power rule times the derivative of this, or you can just rewrite it. Since we're cubing e raised to the 2x squared, we can rewrite this as e raised to the 6x squared, and we can differentiate that. In differentiating that, we get e raised to the 6x squared times the derivative of 6x squared. It's a chain rule portion. So you get e raised to the 6x squared times 12x. Or in other words, you get 12x e to the 6x squared. That's it. Sometimes rewriting it can be easier if it's possible. Okay? Now, for this next one, rewriting it is not possible. So we have r of x is equal to the natural log of x squared, all of this quantity squared. So here we have to use the chain rule. So remember, our outer function is the squaring function. Our inner function is the natural log of x squared. So now we want to differentiate all of that. Using the chain rule, we have to bring down the 2, leave the inside fixed. The inside is the natural log of x squared, raised to the 2 minus 1, and we can stay consistent by putting parentheses around there. But then that was the derivative of the outer function. We have to remember to multiply it by the derivative of our inner function, which is the natural log of x squared prime. Now we get that is equal to 2 times the natural log of x squared. 2 minus 1 is just 1, so we're okay. And then we will have the following. Let's do an aside for this so it won't look like it just popped in out or popped in the middle of nowhere. So let's do an aside. So the natural log of x squared, that should be x squared, all of that prime. We have to use rule 3 from page 1. And if you need to pause the video, go back to page 1, do that. But remember, I said you should have written your rules down, and hopefully you did that. So now using that, we have this is going to be equal to 1 over x squared times the derivative of x squared. That's equal to 1 over x squared times 2x. Well, that gives us 2x over x squared. But x squared is x times x, so we can cancel one of those to get 2 over x. So the x cancels with the square, and we get 2 over x. Well, that's what goes right here, because that's the derivative of the natural log of x squared. Now we simplify. That's what we do now. This is equal to 2. Note that you have another 2 to come from right here. So that would be 2 times 2. The first 2 came from this 2. The second 2 came from that. Then you have times the natural log of x squared, because that's in the numerator, all over x. And that last x that we're dividing by came from here. Well, now you can rewrite it. That's equal to 4 natural log of x squared over x. And just your rules for logarithms tells you that you can bring the 2 down. So that would be 4 times 2 natural log of x divided by x, or in other words, you get 8 natural log of x over x, and that will be your final answer. Now, if you're questioning how in the heck are you able to get from here to here, remember your rules from logarithms that says if you have the natural log, right, not highlight or use the laser, the natural log of x to the r is equal to r natural log of x. That's the rule that we applied going from here to here. Okay, let's do some more examples. These are just, it might be overkill, but it's just to make sure you're comfortable with rules at this point. Okay, so now pause the video and take some time to actually go through these examples. Think about what rules you have to incorporate here. You have this, in example F, you have your function f of x is equal to 2e to the x minus x squared times e to the x. So you have a difference, which means you have to differentiate each part. But differentiating this is not so bad. Differentiating this part is a little bit more challenging because you have to use the product rule. Okay? In G, you have s of x is equal to e to the 4x minus 1 divided by x cubed minus 1. Here, you have to use the quotient rule. The quotient rule combined with the rules you just learned. Okay? So pause the video, work through those examples. So now you've had some time to work on the examples. Now let's work through it and check it. We want to find the derivative. So f prime of x is equal to 2e to the x, because the derivative of e to the x is e to the x, minus, we're going to put brackets here because remember, we have to use the product rule, okay? So you would have x squared prime times e to the x. Remember, you differentiate one, fix the other, and then you add to that the one you differentiated before, you now have to fix, and then you have to multiply by the derivative of the other. Now I'm just writing this step in just to remind you of what the product rule is. So now that's 2e to the x minus bracket. What's the derivative of x squared? Well, that's 2x. So 2x e to the x, right? Because here, the derivative of x squared is 2x, and then we just bring e to the x down. Then you would add to that x squared times the derivative of e to the x. Well, derivative of e to the x is just e to the x. Now, we distribute our negative. We get 2e to the x minus 2x e to the x minus x squared e to the x. And the only thing you could do from this point, because you can't simplify terms, there's nothing to simplify. The only thing you could do is factor out an e to the x. Now, I would accept this is an answer, but you can also factor out e to the x and rewrite it as e to the x times the quantity 2 minus 2x minus x squared. And that's your final answer. Your next example, we have to use a quotient rule. Okay? So, the quotient rule, just to remind you, says that f over g prime is equal to g times f prime minus f g prime all over g squared. Okay? So, applying that rule to where that's your f and that's your g, we now have x cubed minus 1. Use parentheses. If you do not, it's easy to mess up the algebra or make mistakes with that. So we wrote down g. Now we need to write down e to the 4x minus 1 prime minus f, which is e to the 4x minus 1. All of that times the quantity x cubed minus 1 prime all over x cubed minus 1 squared. Okay, so that's just applying the rule. We haven't differentiated yet. Well, we've differentiated using the rule, but we actually need to calculate the derivatives. So we write down x cubed minus 1. And now we need to differentiate e to the 4x minus 1. Well, the derivative of e to the 4x minus 1 is e to the 4x minus 1 times the derivative of 4x minus 1, which is 4. So you can just write 4x minus 1 prime, or you can write 4 minus, as we're now on this portion here, so minus e raised to the 4x minus 1 times 3x squared, because that's the derivative of x cubed. The derivative of 1 is 0, so that part goes away, all over x cubed. That's a cubed. Doesn't look like 1, so let's make it look like 1. So x cubed minus 1 squared. And then we get x cubed minus 1 times e to the 4x minus 1. The derivative of 4x is 4 minus 3x squared times e to the 4x minus 1. Just rearrange the second part, all over x cubed minus 1 squared. And the only thing we can do from this point is notice that, hey, there's an e to the 4x minus 1 here. There's also one here. So we can factor that out and rewrite it. So we'll get e to the 4x minus 1 times the quantity x cubed minus 1 times 4 minus 3x squared. Let's move that over a little bit. give us a little bit more room. 3x squared all over x cubed minus 1 squared. And we can rewrite this as e raised to the 4x minus 1. Here, remember that's a minus there. And here, we can distribute this 4 to each part here. So that would give us times the quantity 4x cubed minus 4 minus 3x squared all over x cubed minus 1 squared. And that's our final answer. So we just differentiated e to the 4x minus 1 over x cubed minus 1. Our last example is we want to differentiate e to the 2x times 4 to the 2x. Okay, so here we need to remember that we're multiplying two different kinds of exponential functions. So we need to remember the derivatives of each, and then we need to apply it. So here, remember the product rule says that, hey, e to the 2x, take the derivative of that, multiply that by 4 to the 2x, then add to that e to the 2x times the derivative of 4 raised to the 2x. Now let's actually find out what those derivatives are. Well, the derivative of e to the 2x is e to the 2x, but times the derivative of 2x, because that's the chain rule portion. Then we fix 4 to the 2x. This takes care of this portion is this, and then we just bring that down. Now we add to that e to the 2x. Now we're differentiating 4 to the 2x. Now the derivative of 4 to the 2x is equal to 4 to the 2x natural log of 4 times the derivative of 2x. Okay? Now this is equal to e to the 2x times 2. So let's put that 2 out front. Where did that 2 come from? That 2 came from just taking the derivative of 2x. That's 2, so I put it here. Now, multiply by 4, 2 to the x. Then we're going to add to that e to the 2x times the derivative of 2x prime, or the derivative of 2x is just 2. So we can write a 2 here. Well, let me just leave it in the order that we are differentiating in. So let's just erase this. So you have e to the 2x. We brought that down. And then you have 4 to the 2x, natural log of 4, times the derivative of 2x, which is 2. And we'll do some rearranging. We have 2e to the 2x, 4 to the 2x. We didn't do anything to the first term. Second term, let's move that 2 up front. So 2e to the 2x times 4 to the 2x, natural log of 4. And if you notice, there's a 2e to the 2x there and here, and there's a 4 to the 2x here and here. So we can factor that out, and we would have 2e to the 2x times 4 to the 2x. But if you factor it out, that leaves a 1. And then we'll have plus the natural log of 4. And this would be our final answer. That's section 11.5, derivatives of exponential functions and logarithmic functions.